Hello, ladies and gentlemen. It is Mrs. Cindy here today, and I would like to talk to you a little bit about work and power. Okay, so work and power, it's lesson 1 in our new chapter 3, okay, of work and machines. So we get to start talking about machines soon, but let's get some background information before we move on. So, what is work? I am actually going to change colors. What is work? So work is a force acting through a distance. And we'll talk about this quite a bit right now. Okay, it's a force acting through a distance. It's kind of the definition that we're going to be using today. Okay, and let's go ahead and move here. Okay, when work is done, anytime that you lift, push, or throw an object, but one more thing, and only when that force only when a force actually moves the object. So the key is, it's anytime, object. So the key is that you have to lift or push or throw something, okay? So when you go to lift something, sometimes you aren't able to lift it off the ground. That would not count as doing work. And of course, you know that you're doing something, but as far as being classified as work, it is not. Same thing when you push something, it is not going to be classified as actually doing work. So that's a major thing. So this is only half the definition right here. So here's an example. Even though I'm pushing on the wall, or this cartoon is pushing on the wall, it is not work unless the wall moves, okay? Not work unless the wall moves. And I want to thank, by the way, Google Images for all of the awesome pictures I have for today's presentation, okay? Today's set of notes. So not work unless the wall moves, unless whatever it is moves. So with that said, okay, there is a work equation, and it is equal to the work is equal to the force times the distance. Sometimes you see this word instead as displacement. So just meaning that you're moving it from one place to another, okay? Work is a unit that we haven't seen before, but force is a unit that we do know. Force is measured in newtons, okay? And then distance will be measured in any of those great SI units, but usually we'll be using meters, unless you're talking about something very small. So let's go ahead and use this equation to see what happens. So how much work do you do when you push a shopping cart and you are applying a force of 50 newtons and you're pushing it for a distance of 5 meters? And so as straightforward as the equation says, force times distance, you would multiply 50 newtons times 5 meters, and you would get a handy-dandy 250 newton times meter. Newton times meter is an SI unit, okay, but we shorten it to be a joule, and we use the capital J to represent that joule. Okay, let's look at another example. Here's an example. Who has done the most work, this person or this person? They are both pushing with a force of 500 newtons. So they're both pushing with the same force. However, you can see that this person is showing no signs of movement. It's a much heavier object that they are pushing versus this person. There's a lot more mass in this object, a lot less mass in here. And so what we would do is, and so they are able to move it when they're moving at 6 meters. So what we would do to do the calculation is we would say 500 newtons times 0 meters will give us 0 work. So that's what the work would look like. Okay, so work would look like 0. So they've done no work, but of course they're sweating. They're look at all that sweat pouring off of them, right? They're sweating like crazy, but nothing is moving. This person, however, is pushing that same 500 newtons of force, and they are moving a beautiful 6 meters. They're able to move that huge ball 6 meters. So the W for this would be 3,000 Nm, or you would say 3,000 joules. Okay, so that's examples of the type of calculations you might see or you might not see. Now, there is a tiny little nuance on that. These people are pushing it in this direction, so they're putting the energy and the force in that direction. However, the little nuance here is that the calculation, it is not, oh, I'm sorry, one thing before I say that, is the calculation does factor in that a heavier object will require more newtons to move. So, so that just means that even when it's a heavier object, as long as you move it, it will factor that in because it requires more force to lift it. So as long as it moves, the work equation will factor in the heavier objects, but the movement has to occur first for it to be considered that. Now, to come back to the nuance of this idea of work, is that to be considered work, the object must also move in the direction of the work force or the work motion. Okay, another kind of way to say this is that the force you exert, or the machine exerts, you could say machine here if you aren't feeling like doing any work these days, must be in the same direction, must be in the same direction as the object's motion, okay, for it to also be considered work. So it's kind of a weird thing, but let's look at some examples of this, what this would mean. So lifting an object is work. And lifting the object is work is because it is classified as work because the force is the upward direction. So it's lifting up. And so the direction of the motion is the same. And so that's why it works. It works as work. That's why it's considered work. So the direction of the motion, both of them are the same, up and up. And then I also thought I would use this to remind you how, even though you guys are young, you know, your back is important. You want it to last for a long time. If you notice that you move close to the box to lift anything heavy, you grab a firm grip, you bend your knees, and you lift with your legs. And if you're interested, there are 1,000 more Google images of even putting it down, the whole cycle of doing that. So just to remind you, lifting heavy objects is extremely important. Use your knees. Let's think of another example. If you're carrying something, so to come back to whether or not it's classified as work or not, if you're carrying an object, meaning that you've lifted it up, you did do work to lift it up, but now you're walking it across, okay? You're moving it across this way. It is not work. When you are carrying an object, it is not work because the force that was used and is being used is lifting the object, holding the object up and holding it against gravity, if you will. That might help a little bit. But the motion is not the same, and so it does not qualify as work. Okay, so just a little detail there. To switch over to power, okay, power, the definition of power, it's a little tricky to get, is the rate, it's a little tricky to think of my own definition, I guess, the rate at which work is done. I was trying to find something where I didn't have to use the new term that you did, and I couldn't. So the rate at which work is done, okay? So when something, an object or a machine, has more power than another, it can get the same amount of work done in less time, okay? So if there is power involved and you're comparing a machine lifting something versus you lifting something, because the machine has way more power if it's a strong machine, then it will get that same amount of work done, that same lifting process done in less time, because it can actually do it, and without, it can actually do it. So with that said, let's look at some other examples here. The equation for power is the amount of work does not depend on the time when you're talking about work, but power is dependent on time. Okay, so this was our original equation for work, force times distance. Now by bringing in power, we're saying that force times distance divided by time. So before, the work was not considering the amount of time it took. Now with power, it does consider that. Okay, so let's look at some other examples here. A tow truck, okay, a tow truck does 10,000 joules of work in 5 seconds. How much power did it use? How much power was required for that? So we plug it into our equation. That power is equal to work divided by time. And so we put in 10,000 joules divided by the 5 seconds. And if you notice, I'm putting in my units the whole time. Okay, when I do that math, I get a handy dandy 2, 0. I don't know why I'm saying handy dandy. I'm very tired right now, so maybe that's why. 2,000 joules per second. Joules per second. What this unit is, and the next slide will talk to us, but that's the unit for that. But power is actually measured a little bit more in watts. Okay, so watts is our unit of power that we use. 1 watt is actually super small, and so when you look at it, this light bulb requires 23 watts. A horse has a, so when you think about horsepower, by the way, and that's why I have this great, awesome picture of this, 1 horsepower, we talk about like an engine, it has this many horsepowers, right? It has one horsepower is equal to 746 watts. Okay, so when we think about machines working, 1 watt is very small. Perhaps when we talk about us running, it doesn't require as much power. But that's just a really cool thing, I thought. A watt is really a joule per second. However, we tend to deal with kilowatts and horsepower. Okay, and horsepower. And I believe that we are done for the day. Let's just make sure. Yeah, we're done for the day. Okay, you guys, so enjoy this. Have fun with your worksheet to help reinforce this material. And I'll see you again.